Hello everyone, this is Sharcnet's General Interest webinar. My name is Sergey Maschenko. I'm from Sharcnet, based at McMaster University. Today I'll be talking about what's new and exciting about Graham GPUs. The Graham supercomputer, one of the two new national systems installed by Compute Canada. One is hosted by Sharcnet at Waterloo University. The other one, Cedar, is at Simon Fraser University. And you see the picture of Graham. I took myself a month ago the official ceremony opening the cluster. There are lots of things which are exciting about this cluster. For example, it has more than 33,000 modern CPU cores, but the topic of today will be the GPU side of the story. To remind you, the realistically only GPU cluster we had so far in Sharcnet was Monk, which had around 100 of Fermi generation GPUs. And here's the list of generations of GPUs. So you can see the newest GPUs we will have or already have in Graham supercomputer are 3 generations newer. Monk is Fermi, then we had Kepler in 2012, then there was Maxwell 2014, which is actually not very interesting. There was no HPC version of that GPU. And Pascal, the ones installed in Graham, were introduced in 2016. Specifically P100 cards. This is what Graham got. 320 of them. Cedar, the other national data center, which will be open at Simon Fraser very soon, has 584 P100, so even more of those. So in terms of generations, so we have 3 generations newer now. I'll split my discussion into topics. I'll talk about quantitative changes, I call them evolutionary changes, and then revolutionary, which is qualitative changes. I'm comparing Monk to Graham. And by the way, you probably all noticed Graham is now officially open for testing since yesterday. You should have received email this morning about that. So anyone can log in there using Compute Canada credentials and try to compile code, submit jobs, and so on. What about evolutionary changes? So I'm comparing Monk to Graham. In terms of CUDA cores, Monk has 448 GPU cores per GPU. Graham has more than 3,500 per GPU, so it's a substantial increase. And mostly because of that, the single precision flops, the second line in my table, is by a factor of 9 larger on Graham GPU compared to Monk GPU. So the GPU cores themselves became maybe slightly faster, but there are many, many more of them. That's a quite important point. I'll get back to that later. In terms of device memory, technically Monk GPU has 6 GB, but the way memory error correction is organized there, it takes up quite a substantial part of the memory, 0.8 GB. Also, it uses some of the compute cycles on GPU. This is not the case on Graham GPUs. It has more memory, 12 GB, and is completely available for programming purposes. And quite importantly, with so many GPU cores, you really want to have good memory bandwidth between device memory and GPU cores, and it's indeed the case. P100 has factor of 3, actually more than factor of 3 faster or larger bandwidth between GPU cores and device memory. This is an overview of 2 revolutionary new things, which I find the most interesting. Both of them appeared in earlier generation Kepler, but because we never had Kepler cluster, I will be discussing them here in this webinar. So the first one is CUDA dynamic parallelism, CDP. It is a new feature which allows one to submit kernels from inside the kernels. If you ever attended our CUDA courses, we run summer schools every year, or if you learned CUDA some other way, so what you learn is that you can only submit kernels from the host code. This is no longer the case with CUDA dynamic parallelism feature. It is not enabled by default. You have to add extra compile and switch. Once you do that, you're allowed to submit kernels from kernels and do many other things which in the past you could only do inside the host code, like calling CUDA device synchronize, things like that. Importantly, to enable this new feature, you have to basically rewrite your code to make use of this new feature. This is not the case with the second new feature, which is hyperqueue. For that, you don't have to rewrite your code. In a prior generation, specifically among the generation of GPUs, there is a single queue, single point of entry of all the workload coming from different CPU threads towards a single GPU. It is possible on Monk to have multiple CPU threads submitting workload to a single GPU, sharing single GPU. But as you will see in live demonstration, without this new hyperqueue feature, there is only one single queue. You don't really get any speed up because there is one queue, so it's executed in the order received, one workload at a time. No longer the case. With Kepler and now Pascal P100 GPUs, one can enable the hyperqueue feature. Again, by default, it's not enabled. I'll show you how to do that. Once you do that, you can see substantial increase in throughput in a few following scenarios. If you do GPU farming and you let multiple processes share a single P100 GPU, or if you run a hybrid MPI/CUDA or OpenMP/CUDA code, again, letting them share a single P100 GPU. It is entirely possible. It can be very efficient, but one has to enable the hyperqueue feature, which is not enabled by default. Now at a little bit more detailed level, let's talk about dynamic parallelism. Here's the basic picture. By the way, it became available since CUDA 5.0. Graham has now CUDA 8 point something. And in terms of hardware, from capability 3.5, which is Kepler. And Pascal is 6.0. So when you run dynamic parallelism, what you have is the CPU thread launching a kernel on GPU. This is your parent grid. It's a grid of blocks of threads. It wasn't possible on Monk GPUs, but it is possible now on P100. Any of these threads can launch subgrids of blocks of threads. And behavior is quite similar to what you have when you have multi-threaded application running on CPU. The master thread on CPU can launch child threads, and the lifetime of the whole code is determined by combined lifetime. So the master thread will not exit until child thread exits. Same is here. The master grid will not end until all the child grids finished. NVIDIA promoted a few interesting applications where it can become very important. One of them is adaptive mesh refinement type of simulations, like fluid dynamics, plane simulation, or astrophysics, things like that. The problem with this research is that you have parts of your volume which do not need high resolution, very smooth flow. And then you have very small fraction of the volume occupied by structures which need a lot of resolution to resolve. In the past, using standard CUDA on Monk GPU, for example, you would have just a choice between overall poor resolution is shown here, so you cannot resolve small details, but you run it fast relatively. Or you want to resolve all those details, then you over-resolve all the parts where you don't need that resolution. So it runs very, very slow. With adaptive mesh refinement simulations, which have become very popular on CPU codes, shown on the right side, your mesh adapts as your simulation progresses. The parts of the flow which have strong gradients are automatically split up into smaller cells, elements. So you get high resolution only where it matters, and you continue resolving other parts with low gradients with much lower resolution. So you are much more efficient. This approach wasn't really possible on Monk GPUs, but with dynamic parallelism, it's entirely possible. One can enable this kind of algorithm on P100 GPUs. But as I mentioned before, this feature requires rewriting of your code, so it can be quite substantial time investment. And another consequences, in the past, you couldn't realistically write a program which would entirely run on the GPU. You would still need to have quite a few things happening on CPU, which keeps submitting kernels, doing mem copy back and forth, doing some synchronization, so on. With dynamic parallelism enabled on P100, in principle, your host can have a single line you call your main or master kernel, consisting only one thread, and that thread would, which is this kernel shown in the middle here, would be doing things which were done in the past by the host, launching different kernels, doing CUDA device synchronized, things like that. So it's entirely possible to write a code which runs pretty much completely on the GPU. It's not necessarily the most efficient way to do it, by the way, but it is possible now. So let's switch gears. I'll explain why, but I'll spend a few next minutes discussing Amdahl's law. It's just a little bit of theory of parallel computing. So this law exists for any kind of parallel computing, not just GPUs, but also CPU, OpenMP, MPI, and so on. And it considers very idealistic situation. In the simplest case shown here, it considers we have ideal supercomputer with infinitely large number of CPU cores, infinitely good networking, huge bandwidth, zero latency. And you have a serial code which you're trying to parallelize. So Amdahl's law states, if the fraction of the code which cannot be parallelized is 1 minus p, p is a parallelizable fraction of the code, and things which cannot be parallelized are purely serial, like input, output, certain algorithm which cannot be parallelized in principle. And Amdahl's law states that in this situation, your maximum possible speed up is given by this equation. So let's consider the next slide slightly more detailed version of this equation, where the actual number of CPU cores is given. Again, the network is considered to be idealistic, but for a given number of CPU cores, this is the maximum speed up you can get. So look at this graph. Let's say 10% of your code cannot be parallelized, 90% can. And pay attention to the yellow curve. You can see as you keep increasing number of CPU cores you're allocating for this parallel job, your speed up is improving, but at some point around 10, 16 CPU cores, you get into a regime of diminishing returns. And then basically you can throw thousands of CPU cores at solve trying to accelerate this problem, and you get almost nothing in return. So 99+% of your cycles will be totally wasted. So Amdahl's law places very strict upper limit how far you can go in terms of speed up, even in an idealistic supercomputer. Of course, the important assumption here is the size of your problem is fixed. And workaround for this limitation was found by Gustafson. There is a Gustafson law saying as long as you keep size of the problem fixed per CPU core, then in fact you can get to a very large speed up. But in many cases you have a fixed size problem, you can't realistically increase it, and then you're limited by Amdahl's law, so-called strong scaling. So why is it important? And how hyperq comes in play? How can it help with this situation? You already noticed Monk GPU has factor of 8 fewer GPU cores than P100. It is relatively small GPU, so it's entirely possible you have a code, a CUDA code, which runs very well on Monk GPU. It can saturate it very nicely, and you really want to saturate a GPU with lots of threads to get maximum throughput. The more, the better, as a rule. P100 has 8 times more cores, so if you take the same code, solving the same problem, and try to run it on Graham, on P100, you might very well see a very nasty surprise. It will probably run faster, but just a little bit, definitely not 8 times faster. So it performs poorly, relatively speaking. It's still a little bit faster, but very, very non-spectacular fashion. Why? Because most likely, in this case, you're limited by Amdahl's law. It just happens that your problem size is relatively small, and you're just not capable of saturating this massive parallel machine which P100 GPUs are. So what's the solution? So hyperq comes to the rescue. In fact, the reason hyperq was introduced specifically to deal with Amdahl's law, because it became such a limiting factor with these massively parallel modern GPUs. And how it exactly can help? Now, instead of trying to use one single program, using a GPU, entirely owning GPU. By the way, that's the way it works, both Monk and Graham. Once you submit a job, you own the GPU. You cannot share it between different users, and there are important reasons for that. And so if your old program cannot use efficiently Graham GPU, the solution now is to enable HyperQ, which is disabled by default, and then to do either GPU farming, and I will show you a live demonstration of that, or if you call this CUDA MPI or OpenMP MPI, just enable HyperQ and see if it helps you. So all ranks sitting at the same node would be told to share the same P100 GPU. So each of these ranks by itself probably doesn't have enough of workload to saturate P100. But if you have many MPI ranks sitting in the same node, sharing the same GPU, you enable HyperQ, and then you might see your throughput increasing quite substantially. And it's very easy to test. Just enable HyperQ. There are 2 lines of code you have to add to your job submission script. No changes to your code at all, and see if it helps it or not. So I'm going now to show you a live demonstration of HyperQ feature on actual Graham GPUs. I have a very simple code, primes HQ, which searches for largest prime number in a given interval of numbers. It's very primitive. Basically, I force it to use a single block of threads at any given time. And what I'm trying to do with that is to mimic a situation with more realistic code, which doesn't have enough of parallelism to saturate P100 GPU. Probably had enough for Monk GPU, but not P100. And I will demonstrate how such a very low efficiency code can have a situation where your throughput increases dramatically when you run multiple instances of your code as a GPU farming, sharing a single GPU. Again, reminder, HyperQ is not enabled by default. But before I do a live demonstration, let me show you the job script, something like that I will use in my demonstration. Especially important for people who don't know much about Slurm scheduler. This is the schedule of Graham, which is very different from older Sharcnet clusters. You'll have to learn how to use Slurm scheduler. You write a job script. And here's an example of a job script when you're trying to use HyperQ for GPU farming. So you have a few S-batch switches at the beginning. You want to use a single GPU, as this line shows. Your runtime is 30 minutes. And I'm asking for 4 GB total of memory for my whole process. Because I'll be running multiple instances of my code, so I'll need multiple CPU cores. So it's like a multi-threaded job. So I'm asking for 16 CPU cores in this switch. The 2 lines in blue, these are the lines enabling HyperQ. These are the critical ones. If you don't put them, your GPU CUDA job will not be using HyperQ's feature. And then what I have here, it's a way to run multiple processes within a single job to do this GPU farming. So I have a for loop. I keep submitting my code. I put it in the background. Very importantly, there is a wait bash command at the end. If I forget to put wait, what's going to happen? All those, in this case, 16 instances of my code will be launched, and then my job will finish instantly. To avoid that from happening, you put wait command at the end, and the job will not finish until all 16 instances of my code will finish with exit code 0 or non-zero. So now I'm switching to live demonstration. So I'm going to use my shell. So I'll try to use Graham GPU. Let's see how busy it became, because now it was officially announced as available. Let's see if it's going to work well. So I'm going to SSH to my login name, sim@graham.sharcnet.ca, or as an alias you can use graham.computecanada.ca. Both work. It's slightly shorter to do it this way. So I logged in. Now I'm inside Graham login node. I'm going inside this subdirectory P100, and here you can see a few files. One of them is the CUDA code I'll be using for my demonstration. Is primeshq.cu. First, I'm going to show how to compile CUDA code in Graham. You have to load the module CUDA. It's not loaded by default. sorry, I forgot to put load, of course. So module load CUDA. So if you say module list, now we should be able to the list of modules, all the default ones plus the CUDA we just loaded. As you can see, the default CUDA is 8044, so one of the most recent ones. Now I can compile my code. I use nvcc -arch, don't forget -arch equal sm_60. So this is the capability of P100. And then I want to do it with optimization. And this is the code. And -o, this is the binary. So that should compile the code. So here's the binary. So here's the job script. It looks similar to the one I just showed, just slightly different. So let's see what's inside. The same lines I showed you before. I'm asking for 1 GPU, which will be shared among multiple processes in the same job. 30 minutes runtime, 4 GB RAM, and I will be using 16 CPU cores. So here are the two lines, as I told you, they enable hyperqueue. So for now, let's disable it. And what I do here, I time my script, another script, which has that for loop I just showed you before inside. And for now, I'll just be running a single instance of my code just to see what's the timing on P100. So this is my job script, and the way to submit jobs on Gram with Slurm scheduler is as batch, and then pass to my job script. So let's see if it's going to work. sq-u my username. It's running, so it's not that busy yet. It's running almost instantly. Let's wait a little. It's finished. And by default, it will produce output file, which looks like this. Just do like this. So it tells me there was 0 threads, only 1 thread, index 0. And the important thing is runtime. It's around 10 seconds. So a single GPU process, single instance of my code takes 10 seconds to run on P100. So let's modify the job script, and let's do a GPU farming, sharing a single GPU, but we have 4 instances of my prime number finding code. The hyperqueue is still disabled. So let's try that. I'm doing as batch, sq. So we are waiting. So R is a state, it's running. It's taking this is the node it's using, Gram 859. So we're waiting. It's already past the 10 seconds we saw before. In fact, we have to wait longer. Still not there, still running. So it's already something quite different. So it takes quite a bit longer. All right, so fine, it finished, and you already guessed. No, by the way, the output is not there. It's not instantly appearing. Now there is the output. And okay, so we ran a GPU farm sharing single GPU. Each individual process would take 10 seconds. When we ran 4 of them sharing 1 GPU, it took 4 times longer, 40 seconds. So there is, again, appearance, there is a single queue, there is no speed up at all, no improvement and throughput, so totally pointless to do it that way. But let's change the script. Let's remove these 2 lines. The first one is just declaring some variable which is needed, but for the second line, we launched the daemon. It's a special hyperqueue daemon. It's a program we run in the background before we launch any of our GPU farming jobs or OpenMP /CUDA or MPI /CUDA jobs or processes. So we're going to save that, and let's try exactly the same job submission. So we run a GPU farm consisting of 4 processes sharing a single P100 GPU. Okay, it's running, still running, and it's done. Interesting. So we had we submitted 4 times more flops basically to process, and it looks like it took the same 10 seconds as it took just one instance of our code. And it's confirmed here. It's again around 10 seconds. In fact, I did some testing. It works the same way, the same wall clock 10 seconds with up to 500 instances of my code. Of course, this is very, very simplistic and very limited code, which I have. Allows only one block of threads at any given time to be submitted to the GPU. But it shows you the power. So you can increase your throughput by multiple times, sometimes by dozens of times, by enabling hyperqueue when you do GPU farming or hybrid computer, OpenMP or MPI/CUDA. So hopefully that was a good demonstration of hyperqueue feature. So I want to mention a few other new features when again comparing P100 with Monk GPUs. First, atomic operations. They exist in CUDA to enable effectively reduction in any other operation where you have to protect shared variables. And specifically, I will show an example where it's used for reduction. And what I highlighted in blue is the fact that atomic add now on P100 supports double precision floating point. This is not the case on Monk, only single precision. I'll show you in a second why it can be quite important. Also, the changes atomic mean and max now support 64-bit integers, but no floating point, by the way. Very interesting point for people who are doing deep learning, machine learning. P100 is really the deep learning beast. It's the first NVIDIA GPU which enables half precision floating point FP16 very, very efficiently. If you remember, single precision floating point performance of P100 is around 9 teraflops per second. If you switch it to half precision, you pretty much double that. So you have 18 teraflop per second deep learning beast as in a P100 GPU. So it can be very, very substantial improvement for people dealing with machine learning. The memory on P100 is stacked memory, and that allows substantially faster bandwidth. Can be quite important in many, because in many situations the bandwidth, memory bandwidth, is the bottleneck for your GPU computation. Some other interesting facts. On Monk GPU, you had to switch to using 2-dimensional grids of blocks or 3-dimensional, not because geometry required so, but because you went above the limit. On Monk GPU, maximum you can have 65,000, slightly more, of blocks of threads in any given kernel. If you need to process more than that, you had to do tricks. You had to enable 2-dimensional grid of blocks or even 3-dimensional just to bypass the limitation, not because your geometry is actually 2-dimensional. This is no longer the case with P100. It has much, much higher limit, 2 billion. So pretty much the only time you need to use 2-dimensional grids of blocks or 3-dimensional when your geometry requires on P100. Otherwise, you can stay 1-dimensional, and for any size of your kernel, you can use 1-dimensional grid of blocks. Interesting point, 32-bit registers per thread now went up from 63 on Monk to 255. Any of you who did some detailed profiling of your CUDA code, you probably dealt with pretty nasty problem when you run out of super fast register memories on multiprocessor, and then the CUDA code starts spilling them into much, much slower device memory. And then all of a sudden you see dramatic slowdown of your performance because of that. The fact that now we have factor 4 more register per thread, and also you can have many, many more threads on P100 GPU. This should reduce this problem and result in better efficiency of your code. And number of concurrent kernels per device. For example, if you're using multiple concurrent streams, you can do it on Monk GPU, but you're limited by 16. On P100, you can have 128 kernels running concurrently. This is separate from hyperqueue, by the way. So let me elaborate a little bit about this new, what does it mean, the fact that atomic add now supports double precision floating point. So let's consider binary reduction in CUDA. So binary reduction happens to be the fastest way to do reduction in parallel. And the way it's usually done, let's say you have 8 elements you want to do reduction over, let's say summation. And what we do, we split this vector in 2 halves, and then we have 4 threads with different colors, purple, blue, green, and orange. And let first thread to take first value from the left half and do reduction with the first value from the second half, and store the result of that reduction again on the left side in the first half. Then the second thread does the same with the second elements, and so on. This is our second step, and then our third step, until we end up having total reduction result stored in a 0 element of your vector. This can only work efficiently as long as you have enough of GPU cores to run all those threads concurrently in parallel. Because there are data dependencies in this algorithm, we have to use some synchronization between threads, and also we have to share values between different threads. In CUDA, you're limited to use this algorithm only within a single block of threads, because block of threads, that's the only place where you can use sync threads and where you can use share variables in fast shared memory. And because in CUDA the maximum size of a block of thread is 1024, even for P100, which means you can apply this algorithm directly only to up to 1024 elements. If your vector is longer than that, you have to do it sort of sequentially. You have to do it multiple times and then combine the partial results together. And the way to do it conveniently is to add these 2 extra lines of code at the bottom. So now we have multiple blocks of threads, each, let's say 1024 threads. It does its own fraction of reduction, and it stores its fractional reduction result using atomic add. In this case, you're assuming you're doing summation reduction. So we designate 1 thread per block of threads, let's say it's 0 index, to take the partial result and to add it to the running total, which is device variable x sum. So all blocks of threads will be contributing to this running total, and at the end you will have total reduction results in this variable. This all great, actually works very efficiently on Monk GPU, on P100, but on Monk GPU you're limited to single precision only, because there is no double precision version on Monk GPU of atomic add. So what you had to do in Monk, if you need to process more than 1000 elements, you had to write multiple kernels. So first kernel would apply the algorithm I just showed on the previous slide for groups of 1024 elements and store them somewhere in the device memory. And then second kernel, which will look similar to the previous slide, would read those partial results and do the final reduction. So this will work for between 1000 and 1 million elements. But if you need to process more than 1 million, you need to write 3 kernels. So it's quite complicated. You have to write lots of lines of code, and not necessarily very efficient, because you have to return control to the CPU, and you have to store intermediate result on device memory, then read them back, and so on. So not the perfect situation. The good news is on Gram GPUs, even if you do double precision, 64-bit floating point, you can use this nice hybrid approach. You do binary reduction at the lower level, and at the high level you just use atomic add, which now on P100 can be applied both to single and double precision floating points. So your code is much simpler, or only 1 kernel, works very efficiently and very flexible. Between 1 and billions of elements, the same kernel can be used to do the reduction.